Okay, thank you for the invitation. I'd like to thank the organizer for this very nice conference. I learned a lot. And also, I'd like to say that I don't have to give the talk because Jianqing already finished all my talk. Okay, so this is about the high-dimensional generalized linear model for dynamically dependent data. It's not surprising I'm talking about dynamic dependent data because I'm doing research in time series. So that's the main reason I did this. A joint work with a PhD student, Yifan Han, and my colleague, Wei Biao Wu at University of Chicago. So when I saw the program, we put me and Jianqing in this finance type of program. I suppose we are related to some type of financial econometrics and in business school. So we start thinking about, you may ask, what's the general linear model had to do with the finance? What's the connection there? Well, Jianqing already mentioned a lot about big data in finance. Big data also quite common in finance now. For example, Jianqing talked about high-frequency type of finance. We'll talk a little bit about that too. The other one you can think about is a global marketing or either global investment. You like to think about assets of many countries and many regions, and you like to analyze all of them. They are all big data now. Now, if you listen carefully, general linear model, it really plays an important role in deep learning. All the network, a lot of activating function are really the logistic regression. And also there are many applications in finance. Logistic regression or the general linear model is useful. For example, in the credit risk, it's talking about amount rating a company. You divide them into several categories, and how do you model that? Those are the general linear model. So in that sense, quite relevant. I will show an example about how to use a general linear model in this type of high-frequency trading example. There are many other examples you can talk about. So general linear model is not that special and can be applied in finance in many other areas as well. So the motivation, I will give the outline of my talk, is the motivation that penalized estimation for the high-dimensional problems. Those are applied to regression, general linear model, to any estimation. You can think about that. The end thing I like to emphasize is general linear model for the dependent data, because that's the main point of my talk. And I like to mention about how to quantify the dynamic dependence, also how to quantify the cross-dependence. All those lasso type of method, Jianqing alluded to, the lasso regression can easily break down for the strongly dependent time series data. But so you have to, for that to work, you have to quantify what type of dependence you allow. Cross-sectional, also dynamically, what type of dependence you can have. And Jianqing did a wonderful job about robust estimation. In fact, we adopt his idea in this talk as well to do robustification so we can obtain a better result in terms of prediction and so on. Oh. Now what happened now? Now I'm upside down now. Can I talk like this way? Well, anyway, I will talk about estimation and talk about applications. Okay. In any case, now even I don't know what I'm going now to do now. This is just a review about how dimensional estimation, how do I review that, and just to lead you to understand from a theoretical point of view, to me, there are one piece, something like missing. In the regression concept, there are many methods about penalized estimation. We talk a lot about lasso, and there are some other methods like group lasso, or estimate and the SCOT type of method, they allow for the penalized function. And if you have a dependent data, the time series data, the traditional lasso has also been generalized to the general case. Okay. And for example, Basu and his associate and his advisor talking about if you have a sub-Gaussian type of process, you can generalize the lasso method to the time series data. Wu also talk about some type of generalizations, and there are a lot of sparse autoregression model. G.B talk about band metrics. That's one type of sparse type of methods. And the student Han and I did a little bit about how to generalize the lasso type of method for the dependent data. That's a pure time series models. For the generalized linear model, people also generalize penalized type of estimation to handle the generalized linear model. There are several references. That the one thing missing is people had not really working on generalized linear model for the dependent data. So to me, that piece of information is missing. So that would like to do to study this type of thing. How do you do generalized linear model if you have dependent data? What type of methods still available? What condition you need to make that work? So that's basically the thing I like to talk about. Now it's all stuck now. Okay. So basically, from my point of view, is we have this missing information, and we like to fill the gap. So you can apply this high-dimensional penalized method to the generalized linear model. It turns out you can apply that, and financial application is one of the obvious area you can do applications. Should I wait for a minute? Just like last night, there's the opera. Anyone want to sing? I'm not a good singer. I cannot really sing. But if someone want to do that or dance, yes. Now, while you're waiting, I can sometimes relate to answer your question a little bit about the partiality squares. You can apply the concept. Your diversify will be still useful in the partiality square. The only difference, the partiality square and the lasso, something like you mix together, because partiality square combines the variable selection and the prediction together, not only just the factor. Sometimes people like to do factor for interpretation type of purpose. But you can do that. Partiality square, in some sense, is a very greedy type of method to do variable selection. So it still can okay. I'm sure the robustification will be useful. That I think is my answer. Oh, it's good. Okay. Now I think I can continue now. So the basic is regularization already mentioned that this sounds like a piece of missing link in terms of theoretical part that we like to fill in this work. Like heavy tail and outlier robustness, those are all important issues. And Jianqing is the one start to address this in the high-dimensional case. Is very important. Outlier happen all the times. Missing value, outlier, those are all quite common. The heavy tail distribution, Jianqing already show you a lot of high excess kurtosis. In finance, those can be quite high. So what I like to do is something like extend the robust regression or robust time series literature to this high-dimensional case. Jianqing already mentioned some of that. We actually use the idea, especially from this one, the truncation, that's the one we like to do. There's also a paper about the robustness equation, either convex or non-convex type of models. So the problem I'm talking about is we have observations. We have observation. This xi follow the tradition. Those are the predictor or the regressor. Yi will be a scalar, in this case, generalized linear model type of variable. We're still thinking about, you relate to that, the mean, the expectation of y is really the function of the linear function of the variable. This beta not means a true parameter. We define some loss function, because the loss function plays a role here. The estimate is penalized. That's a Lasso type of penalty, and you like to do loss function, and we define loss function because we assume the mean function linearly related to the predictor. We have the excess risk, because the loss function, this you know the true parameter, that's your expected loss, and this is excess loss, because we estimate the parameter, you have that. So the distribution of y is follow this exponential family. That's the general type of exponential family distribution. This R and B are non-function. This mu is a canonical variable, and so on. So the loss function is all general. We put in this way. This H and R, this already know the depend on distribution function. This H is another function depend on the mean. Those are, you have to satisfy some type of uniform continuity condition. We'll mention that in a moment. For the high dimensional time series, I give a more specific way to quantify the dynamic dependence and the cross dependent and so on. For those you understand in the time series analysis, those are basically in the literature, people use a mixing condition to quantify dependence. Here, we like to use for the work by Weibia Wu to quantify that more directly based on what people call the impulse response or cumulative impulse response. Those are the way in time series analysis you can see how that impacts that. So I will be the time. In the case, I will be the time, and xi is the p dimension. You can think about those are the high dimensional innovation or the shock. Y is also depend on time dependent and so on. So J will be the J's predictor, and you have the Q's norm. You define in that. What is this one? This is a notation rather simple. For those you understand the time series analysis, this basically is the I's impulse response. What will happen is you replace F star, you replace this shock. The original one is this shock. You replace this shock by this one is identical IID copy of that. And see what the difference in terms of time series, because this 0 is the I's time, so that's I's impulse response. Now we quantify in the Q's norm. That's the only difference. So for the Y, we also quantify that. So that basically is a impulse response function. You like to quantify that. For the high dimension, we like to quantify not the individual leg is important, but not sufficient. So we like to thinking about cumulative impulse response. So at M on, you can think about those are the cumulative impulse response will be finite. Otherwise, it become like unido type of time series, then Lasso method will break down and so on. So those are the quantification. That's for the time series, the J's time series. That's for the output response. We also have that. Now to derive the theorem, to prove some type of consistency, that type of method or asymptotic property, we have to do, we call the distant adjusted norm. Basically, this is the way we like to assume something exists. So this cumulative distribution, this one will be bounded. The same thing for the y. This is exponential decay. This is thinking about polynomial decay, and you like to do this type of thing. So basically, we like to use this type of measure. It's a cumulative response to quantify the dependence. And this is where the decay, the dependence, some sort of like dependence in the polynomial rate. This is an exponential rate. This is a stronger rate. Under this one, you obtain a nicer result, and so on. For cross-dependence, we use the same type of idea. This for I is time, So you're thinking about at time, you cross dependence, you quantify by the Q's norm. Again, you cumulative them. And this one is for the dependence. Again, it's a polynomial rate. This will be the exponential rate. Once you have this type of rate in hand, you can try to derive theoretical result. That's basically what we have. So those are to do the robust estimation. What you like to do is a truncation tau already here. Ciencia already mentioned that. So in this particular case, you think about robust type of estimation. This is just for estimation, not for prediction. So you truncate the xi. Xi truncate by, Ciencia already mentioned that we truncate for every time series. You can do that, and you can select that. In real application, those penalty parameter and the truncation parameter, we do that by some sort of like Fourier search and looking at the outer sample type of method. In the simulation, I can do the in real application. We use some of the outer sample to find the good choice of lambda and the tuning parameter. So let me summarize the contribution, just in case you fall asleep, to tell you what we did in the paper. The first one is we provide asymptotic behavior for the estimate the general linear model coefficient and the excess risk. Under the original time series data, also for the shrinked or truncated heavy tail time series data. Under the bounded moment conditions, and the noise and the covariance, the robust type of estimator almost achieve the same error rate like sub-IID case. I'll talk about this almost a little bit if you're interested in that. The dimension P can be as large exponential C. Okay, can be quite general as well. This depends on if you have exponential decay, if you have polynomial decay, then you can have P can only have a polynomial rate and so on. For the robust estimation, you apply to the usual linear regression high dimensional time series. I think Jen Cheng already mentioned that. We just do that. For the weakly temporal dependence and heavy tail type of distribution, you can achieve the minimax optimal in the L2 type of way. You can do that. So those are, in some sense, is quite useful, encouraging result. I don't have the time to talk about this part. It's some sort of to develop the general linear model for dependent data. We have to develop new concentration inequality so you can extend the result in the IID case. So here are some assumptions. We have to be convex type of function for the loss function. You also have to be some continuity condition. So the Lipschitz in the property, you can separate in this way, so you can handle that. Also, there's a time, in the time dependence, this i's time, the case time, you also satisfy this type of condition, so you can handle that. There's some justification about that. Assumption 3 is needed for the temporal dependence, about the temporal dependent. 2 and 3 are needed for the concentrated inequality. The assumption, you can easily see that, like this loss function, it satisfies the condition. So let's say the condition is not, say, very strong, because this type of thing we need. The next condition is called marginal condition. Is in the neighborhood of a true parameter. This, we have to have a strict convex function, so the excess loss is bounded below by that. And also, this is an important condition related to if you have a subset of that and the complement of that is satisfy this condition. This basically it restricts the eigenvalue condition for you try to estimate, develop asymptotic result for the lasso type of regression. You need that. Okay, now define some type of, for the general linear model, we define this oracle parameter, beta star. If you minimize this one, you define it this way. And this is the minima excess risk. You can define that. Those are the non-zero coefficient. That's how many non-zero coefficient you have. And you can have this G is a convex conjugate of the bounded function, convex function I mentioned earlier. So From under those complicated conditions, you can establish this type of property. You can establish the L1 norm and also the exit risk has some type of stuff. So the dependent condition depend on two cases. One is the short-range dependence with polynomial decay rate, I already mentioned. The other one is short-range dependence with exponential rate. So these two types of rate give you two different results. So the implication is for the exponential moment condition, you can take lambda in this way, the penalty function, and you can see that the p can be as large as the exponential one. For bounded moment condition, you can only have polynomial. The p cannot really extend too big compared with the sample size. For robust estimation, we have to have some moment condition. So those are some moment condition. The y has to be exponentially decay. Then you can obtain this normalized type of, that's a truncated estimate, and you can obtain similar type of result. That's basically what we did. Okay. Those are for the general linear model. You can apply this robust type of method to the regression, to the general regression. The general regression here for the estimation, you actually truncate in two ways. Not only you truncate the predictor, you also truncate the dependent variable. In this different tau, you can do that. And under certain condition, the moment already mentioned that, and you also have to be cross-dependence. You also need some type of constraint, and you have needed the weak sparsity condition. Under those, you can establish this type of result. One point I mentioned almost is here, we cannot obtain 1/4. For IDK, this rate can be 1/4. Here we only have 3/4. So that's the dependent caused by that, and we haven't really figured out a better way to improve that. So that's the thing we had. Okay. So with that in mind, now we talk about simulation to show you what it looked like in terms of simulation study before I go to the real example. So for the time series part, we generate I the time, j the time series. So this will be, well, this will be j, not I. And here, for j is the autocorrect AR1 type of model. Try to avoid the weak, very independent case. So we some sort of truncate in this way to make sure there are serial correlations. For this noise, we use heavy tails. So that's the t distribution of 5 degrees freedom. The other one is log normal. Log normal, here, this time series part. You have to mean adjust it because this assume mean equal to 0, but you can assume that you can adjust that. You can have that. For the cross-sectional dependence, we use this type of method people use. The correlation, decay, either far apart, the decay, and so on. So that's the way you generate the underlying time series. Then you observe, your predictor is obtained this. So even though you generate these independent processes, but because of this correlation, they are correlated in that sense. Okay. So that's the thing we have. For the logistic regression, we have 400 dimension in our simulation, 400 dimension. The probability of that equal to 1, given this polynomial here. This beta 0 is here. We have 400 dimension. The first 20 are 3. We always use 3. Jianqing also uses 3. I was surprised. Maybe we are from using the same 3 here, the same type of structure. The sample size from 200 to 3,000 to show that correlation. That's a cross correlation. Is about this cross correlation 0.5 and so on. We have 5,000 iterations. For each iteration, we generate 500 extra points for the out of sample prediction. Okay, so that's the out of sample prediction in the simulation. For each covariate, we center that the mean equal to 0. And this lambda and tau, we select by independent type of cross validation to find out. Then once we select lambda and tau, we apply to every iteration, we can do that. So the criteria we try to quantify how good the out of sample prediction, we calculate the L2 error norm and also L1 error, and the false positive rate. That's basically the noise variable got selected, and also the false negative rate, the important covariate got missed, and also the one-step prediction error. This is a misclassification rate because the response is 0, 1, and so on. So here is the regression part. You can think about two types of noise, the t-distribution 5 degrees of freedom. That's the usual lasso type of method. That's a robust lasso. This is a log normal innovation. And for the time series generated by that, the lasso method and the robust type of lasso. You can see that when sample size is small, this is 400 dimension, sample size is 20, you can see that they are not really that great. As time goes, as the sample size increase, you can see the improvement. Okay, you can see the improvement. For example, want to get to typically you think in a 400 dimension, you get to 400 observations. Those are all become more reasonable. Beyond that, you can see that if you get more observation, the sample size, for example, the false negative rate becomes 0 once you have enough sample size, and the false positive rate is sometimes not really going away. You always have that, but it's not really increasing that much. You can see that they are roughly stabilized around 4, and the out-of-sample prediction, the error rate is about 17%, and so on. So that's a logistic regression. Okay, you can do that. So basically, you can see that the result is something like in agreement with the theorem we tried to obtain. As sample size increase, your performance improve, and the robust estimator actually work quite well. Okay, in terms of estimation, I think the main reason is it provides you a better estimate of the beta coefficient. And out-of-sample prediction, we don't really robustify the X. You just use original predictor to do prediction. So that, I think, is the main reason. So the false positive rate increased slightly with a sample size, but false negative rate approached 0 as sample size increase. Now, for the linear model, the time series part, we actually increase the noise, doesn't multiply by constant 0.1 or something in front of that. So the same type of model. Generate the time series is the same type of method to generate time series part, but noise become bigger. The time series part, now this is a linear model now. So we have this innovation here. And this innovation, we actually take t degrees of freedom, 3, push it to the boundary, and we time 20 to that. So the standard deviation of this noise is about 35. We also push this log normal, time 20. So the standard deviation, the mean is here. The mean has to be adjusted, subtract the mean. The standard deviation about 12. So that's what we did. We generated that. Again, 400 dimension. The sample size started at 50, get to 2,000. Again, we have 5,000 iteration. And for every iteration, we generate 200 data points that to do out-of-sample prediction and so on. So here is the result for this particular simulation. You can see that when sample size is 50, those are not really reliable. Okay. Sample size 50, you have 400 observation with serial dependence. Those results are not really that great. When you gradually increasing, when the sample size is increasing, you become much better now. Okay. For example, when you get to 800 or get to 400, typically when the 400 dimension get to 400, the theoretical value is, I think, about 35. And you get to about 37, 36. This theoretical value, about 12 point something, you get to about 13. So those are become reliable now. So you can see that once you get to about 1,000 or 2,000 observations, and I mentioned this one theoretical value about 34.64. This actually, maybe due to rounding error, is smaller than theoretical value. Those are close to the theoretical value. So in some sense, robust type of estimation, actually, in this particular simulation also, the robustified version performed better than the regular one. So that, I think, the truncation or the heavy tail type of stuff will be useful in this particular case. Again, the simulation tell you, similar like what we had before, the result also shows that the robust estimator outperforms the non-robust one. In this particular case, especially for the heavy tail distribution, if the time series noise t distribution is 3 degrees of freedom. So that's the important message. For this type of method to work well, for the regression model or for the logistic general linear regression model, for the dependent data, based on my own experience, the sample size probably should be the same like the dimension. If you have high dimension, too few parameters, and too few observations, the time series case are not really that informative. Okay, so typically, to me, based on my experience, sample size probably equal to the dimension. That seems to, for you to start to work, see the reason very well. For the log normal type of distribution, this asymmetry type of noise, the false negative rate seems to be higher than the false positive rate. Okay, and this rate are not really small when the sample size is small. So those are the simulation results. Now let me talk about high-frequency trading. It's not really talking about a lot of stuff about estimate covariance metrics. We talk about predicting the transaction-to-transaction price change. So this is a particular stock I look at. This is about Walgreens. Walgreens is a convenience store in the state. It's quite big, a drugstore, convenience store. And this, for this particular day, last year, I actually do this data set for my MBA time series class. So I just use this one to happen to demonstrate the point. So during this day, we have about 30,000 transaction by transaction. And the observed price, I call that Y star. You can, because the trade by trade data, we do have the observed price. Okay, we call that Y I star. The TI is the time duration between i's and the i's minus 1 trade, because that the duration between that is measured in milliseconds, because that's measured in milliseconds. 1 second is too big, one measured in milliseconds. The volume is typically regular round lot about 100 share. We just divide that by 100, so that's the size is important. Now, since this one is discrete, even though theoretically it is a continuous variable, but observed value, actually it can be classified into several categories. For simplicity, I classify them into 7 categories. Broadly speaking, for this particular data set, this one, the transaction to transaction, no price change is about 70%. That's rather common. And this one to this one is about 13, 14%. Beyond 1 cent, the percentage of that is very small. That's a fact. Okay, this happened to most of the stock. Also, in the US today, this high-frequency trading for the New York Stock Exchange, high-frequency trading is about 70% of all the transactions. So it's not a small number. About 7% all the transactions are high-frequency tradings. So this is involved, the money involved is quite substantial. So what we like to do to fit into the general linear framework, we like to predict which category for the next transaction price. So that's what I like to predict. And we create some categorical variable. Those are the categorical variables. So we create a categorical variable, 7 category. I have 6 dummy variable to integrate the category. The X variable I use is the categorical variable, the true price change, the duration, and also the size. And for the past several D of them. I have about 30,000 transactions. I reserve the last 2,000 transactions for the out-of-sample predictions. So the method we try to do, we compare with the traditional method in finance. The most commonly used one is the auto-probability model. Those are Hausman Lowe and McKinney, they proposed this one. In some sense, this probably is the state-of-the-art people use if you like to auto this type of stuff. You can also use machine learning, the deep learning type of neural network. You can do that. Long Chen and I, we try to apply that on this data set. You will see the result. We also use, based on the result of this paper, we use a lasso type of method, multinomial logistic regression. We also the robust lasso type of multinomial logistic regression. For the first two, as I did before, we only use the d equal to 3. For this two part, we actually d equal to 16, so we have the x dimension will be higher. We also include, for this one, we also include the two-way interaction, some of the two-way interaction in there, so the x will be high dimension in that sense. So that's the forecasting tabulation, 2000. This is a predictor category, that's a real category. And in this particular case, that's an auto-probing model. Auto-probing model only predicts category 4. In some sense, it fails to predict any change. It just say there's no price change. And not surprising in the sense because in the estimation period, no price change is about 71%. And this prediction, this one is the only proper prediction. This is a correct prediction for the auto-probing model. That's the general model people use in finance, and it's only about 71.85% correct prediction. In the sampling period, this one about 71.3%. So basically, auto-probing model failed to predict in this particular case. You look the neural network type of procedure. We have 27 input. I assume that only one hidden there with 10 nodes, and you predict this one. And actually, this not really improves substantially. You can think about almost 1% improvement. And this 1% improvement actually is quite important, especially this like drop more than 2%, you predict 3 correctly. Okay. So those are the neural network. If you use a method we talk about, multinomial lasso type of regression, you can see that the prediction actually is much improved. Even though the probability of correct prediction is, in terms of percentage, you don't see a lot. But this is purely counting the numbers. You counting the money involved, those are actually improvement are substantial. So that's the thing I like to mention in this type of regression. Use a robust type of method, it turns out to be similar, no big difference. It's the same type of correct prediction. You can also see that the predict this one, those are important correct category because you increase by more than 2 cents for a transaction, they increase by more than 1 cent, and so on. So you can see that those are, to me, those are important improvement. So that's probably tell you in the general linear model can be applied to the dependent data, and you have some applications. So in this particular example, based on my experience, the auto-probing model failed in this particular example. It just only predicts the no price change. In reality, there are price change in different sense. The deep learning seems to improve, especially not all the category, but robust and lasso and robust lasso with the regression and multinomial type of model. It seems to improve, especially the extreme category, it can capture that. So that, I think, is the important improvement in this particular exercise. So to conclude, this some sort of general estimation method continue to work for the dependent data, but only weak dependent data. Okay. You cannot have strong dependent. So that's what I mean is this type of method continue to work at short range dependence. Okay. The robust estimation seems to perform quite well in our experience. So this is quite encouraged. It's nice to hear Jianqing talk about his result is also very encouraging. So robust, I think, is a good way to go. There are many questions remains. we talk about, Jianqing also mentioned that, I also, based on my other work, you can say that lasso can easily fail. You have strong serial dependence. If you have strong serial dependence, lasso completely miss some of the important variables. The first first negative rate will be quite high, first positive rate will be quite high as well. This question still remains, how about long-range dependence? We established for the short-range dependence, we understand the strong dependence fail, but however, between the long-range dependence, that can happen in many applications, but we still unknown. Okay, so that's what I like to talk about. Thank you very much.